Welcome back to our channel. In last video we have seen work done with considering clearance volume, again volumetric efficiency in case of reciprocating compressor. In this video we will see multi-staging of reciprocating compressor. Okay, so let's start. Multi-stage compressor or multi-staging in reciprocating compressor. Here, in case of multi-staging, delivery of one compressor is given or supplied to inlet of another compressor. That is, here compression in carried out in stages. So we have shown here diagrammatically. So we have taken air from atmosphere. So there are more than two numbers of compressors in case of multi-staging. Lower side compressor is called as low pressure compressor. High side compressor is called as high pressure compressor. In low pressure compressor, we are taking air from atmosphere compressed to some intermediate pressure. Then there is the intercooler. We'll discuss later on what is intercooler. And in intercooler, we cooled that compressed air and in passed to second stage. That means delivery of one compressor is suction to another compressor, and in this way we have delivered this air to final stage. Okay. So question is, why to carry out multi-staging, or what is the necessity of multi-staging? We will understand it by it on PV diagram. Suppose instead of multi-stage we have using single stage compressor. Air is entering at pressure P1, we are compressed to delivered pressure P2. Okay, and there is, suppose say, clearance volume is there, the clearance volume Vc, then this will be your swept volume here, and 1 2 3, after that expansion of residual gases here up to 0.4. Then this is our effective swept volume. This is the effective swept volume. Suppose requirement of pressure is increased, then we have taken air at same pressure but delivery pressure is more. Suppose say that it is a 2 dash. Then from this, when we are delivering, clearance volume is fixed, so up to this point we deliver, this is 3 dash, and after that according to same law there is expansion, it is 4 dash. Now again say pressure is increased or delivery pressure is increased, then our cycle will be T double dash to 3 double 2 dash 3 double dash. After expansion point will be 4 double dash here. So as this pressure is increasing, or this pressure ratio P2 by P1, this ratio as increasing, then our effective swept volume is continuously goes on decreasing. Initially it is from this length V1 to V1 to V4, then in second case it is V1 to V1 4 dash, then last case is V1 to V4 double dash. That means as pressure ratio increases, in case of single stage compressor, volumetric efficiency decreases. Then to overcome that, we are using multi-staging. In multi-staging, as we have discussed, there are low pressure compressor and high pressure compressor. Here just forgot this intercooler, will consider only low pressure compressor, then delivery to high pressure compressor. We are not considering here intercooling effect at this stage. Now we have taken air from atmosphere in compressed, then there is this is suppose say clearance volume Vc, then air is delivered to intermediate pressure, so P1, this is suppose say intermediate pressure P2 here, and then after this air is delivered to second stage compressor. So here we are deliver this compressor, then again it is compressed to second stage and delivered. Now when it is delivered, after delivering to second stage, it will expand its own. So this is 3 4 dash, and here again suppose this is a 2 double dash, and after 2 double dash compression up to 3 double dash, sorry 3 dash, then till so this is the say 1 dash, then this is a 2 dash, and suppose this is a 3 dash, and after 3 dash it will expand to 4 dash. That means if you consider same pressure ratio here, then volumetric efficiency in case of multi-staging is more than in case of single stage. Now again, if you want to increase pressure ratio, then just add another compressor here, then delivery of this second compressor will be the next pressure, and again there is cycle here. But increasing this pressure ratio or pressure of cycle is not affecting volumetric efficiency here. So volumetric efficiency remains unaffected by increasing pressure ratio. So this is the first advantage of multi-staging. Okay, now let's see just intercooling. So what is intercooling? This word itself says inter and cooling. It means cooling at intermediate stage. It is intercooling. Cooling of compressor air at intermediate state is called as intercooling. It is carried out in intercooler, and it is just working at constant pressure. Here suppose air is entering here to intercooler from state 2 and delivered to state 2 dash. Then for cooling purpose there is a cooling media. Cooling media can be air or water. If it is air, then intercooler is called air cooled heat exchanger. If it is water cooled, then intercooler is called as water cooled heat exchanger. Suppose there is a water, then amount of heat rejected by air is equal to m air Cp of air, then temperature difference, it is T2 minus T2 dash, that will be equal to, this is the heat rejected by air in intercooler, and it will be absorbed by water if it is water cooled. MW Cpw T2W minus T1W. Okay, so this is the energy balance or heat balance in intercooler. This process is carried out at constant pressure. This is the intercooler, and let's see what is the effect of intercooler, or what is the advantage of adding intercooler here. For this derivation, for this explanation, we are considering there is no clearance volume, or we are neglecting clearance volume. That will be more easy for understanding. Suppose that we have using multi-stage compressor, then from first stage of compression 1 to some intermediate pressure, we are delivering this air to 3 point here. Then as there is no any clearance, so total amount of air is delivered to next stage. Then from same point it is compressed again to high pressure. Okay, and here there will be shape volume start sucking air at from this point. So total V1 is here Vs, as there is no any clearance volume, and work done is work done in first compressor plus work done in second compressor. Now consider we are used intercooler there, then we have suck or will suck air at pressure P1, deliver compressed to point 2, then there is intercooler. Okay, there is intercooler which cools air at constant pressure. That means at constant pressure there is a cooling up to point 2 dash, and after this it is passed to second stage compressor, and again it is delivered to second stage compressor. Then after this point it will then compressed to delivered pressure P3. Okay, delivered pressure P3. So here there is a saving of this area. Again we know that this area represents work consumed by compressor, so saving in this area indicates there is a work saving in compressor. Okay, so that means by using intercooler we save work done in case of multi-stage compression. So this is the use of intercooler or use of intercooling. And there is a term perfect intercooling. Perfect intercooling means if outlet temperature from intercooler is same as that of inlet temperature of air. That is, if this T2 dash here, this T2 dash is if equal to T1, then the process of intercooling is called as an intercooler. It means if we join this simply, if T2 dash is T1, intercooling is called as intercooler. That is, if we join this line, then this is this temperature and this temperature is same, so this process will represent some isothermal process, and in this way this process T3 dash. Again this on this curve all the points are having same temperature, then the process is called isothermal process. So next point is to find out optimum intermediate pressure for minimum work consumption. So we have know that by using intercooler there is a work saving in multi-stage compression. Then what is the optimum pressure ratio to getting maximum work saving or minimum work consumption? That is the derivation. Before that, let's see first. Again we are assuming here perfect intercooling for this derivation. So remember condition is perfect intercooling. Suppose air is taken at pressure P1, it is compressed up to point P2. Suppose initially this up to pressure P2, then in intercooler, if intercooling is perfect, it is cooled to point, suppose say T2 dash here, then again here compression is taking place. So amount of work saving here is this much. This much area represents work saving in first case. Now suppose our intermediate pressure is reduced to some value here, then and if we join this T1 point then T2 point, then this process representing intercooler, and if we join this line up to high pressure, then 3 dash will represent this 3 2 dash in 1 path represents isothermal process here. Now suppose if we reduce this pressure to suppose some lower value intermediate pressure, then this T2 double dash to this point, or by isothermal cooling we will get this point as outlet of intercooler. Then again there is a compression to high pressure, then work saving is this much only. Work saving is this much. If you consider that instead of 2 we have got intermediate pressure to 3 double dash, then after there if there is a perfect intercooling, then point or outlet will be at this point, and then compression, then work saving will be this much only. So from this we can conclude that when pressure ratio intermediate pressure is low, then also work saving is less. As we increase pressure ratio, we got maximum work saving, and again if we increase this pressure ratio more, then again clearance, then again work saving is less. So if we draw curve, this percentage of saving of work against pressure ratio, this is P1, this is a P3. If we vary P2, when P1 is equal to P2, then there is no any compression. As we increase pressure ratio, work saving potential is increased, attains maximum value, and again it is decreasing. So we got at some intermediate pressure, P work saving is maximum, and this is called optimum pressure, and corresponding pressure ratio is called as an optimum pressure ratio. Okay. The derivation of optimum pressure ratio we'll see in next video.